This video is about E1 elimination reactions, and I find it a little strange that Professor Pelkey illustrates the first reaction for E1 on his handout with this particular setup. And that's because if I were to look at this in the abstract and say what kind of reaction is likely to happen here in a predict the product sort of way, I would first write down an SN1 type substitution reaction. In other words, I might expect that to be the first thing that forms. Now, it is the case that E1 elimination can also happen here, and so we can illustrate it, but generally speaking, I think of E1 eliminations as being the reaction that happens when all other reactions are slow. And so if an SN1 reaction is going to be faster, then you're going to make some SN1 product. Now, it is the case that E1 elimination reactions tend to be really messy, so you're going to make lots of products all of the time. But if I wanted to bias this setup toward an elimination instead of the substitution, what I would have in here is some heat. Heat has a tendency to send things in the direction that we want. Or if you were to add some acid to make the nucleophile, the water, substantially worse, that also would tend to bias you in the direction of elimination instead of substitution. But let's talk about the mechanism of this reaction. So the first thing that's going to happen, of course, with this tertiary substrate is the chloride's just going to plain leave. And that will lead to the trigonal planar carbocation tertiary intermediate and Cl- floating around. Now, of course, the most likely scenario at this stage is that the Cl- just simply adds back in which case you go back the way you came. And if you're searching for what else could happen, my advice is always to take reagents that are over the arrow and draw them out in sort of standard line angle formula. And if I have the water floating around, then what I might suddenly see is the possibility for a water to go ahead and attack the carbocation directly. And the result of that orange arrow would be this protonated water species, so basically a protonated alcohol. But of course we have water as the solvent, which means I can invoke it more than once in any mechanism if I like, because it's the solvent. And what that would do is then potentially deprotonate this, leading on to the product that I already described as the one that I expected to happen. So if the chloride reattaches, you go back the way you came. If the water instead attacks, you go this way and you end up making the alcohol instead. And again, this would be sort of an SN1 type process. If you're stuck in a mechanism and you're trying to explain something, then another piece of advice that's really helpful is to draw out any implicit hydrogens explicitly and see if that sparks any ideas. And so now you can see that this is a set of beta hydrogens. Of course, the alpha position now has a carbocation on it at the moment. And so the last set of arrows that I might draw would be that what if the water, instead of hitting the carbocation, comes in and bumps into one of those hydrogens, and when it does so, the carbon-hydrogen bond, the electrons in it slide over to become a double bond, and then that goes directly onto the product. So we now have carbon-carbon double bond between the alpha carbon and the beta carbon as a result of this water attacking the beta hydrogen. The key features here, as far as I can tell, are that you're making a lot of different potential products, and you're only going to funnel your way here if there are some sort of biases happening. But, you know, the chloride can leave, that will definitely happen, and you have this equilibrium state where the chloride can re-add, and you go back and forth the way it came between starting materials. Water could add, and that would be a reasonable substitution pathway, which would lead here. And of course, in the presence of some acid, this could become protonated and go back the way it came. And so we're just kind of in this equilibrium area all over the place. And one other thing that can happen is that the oxygen can come in and attack this hydrogen, causing the electrons to kick down and making the double bond, and having the water floating around nearby as a byproduct. Or in this case, it would actually be the H3O plus as drawn. And maybe this one's less likely to go back the way it came because of the conditions. But in any event, when you have an E1 elimination type process, what you're always going to have is a mess of potential reactions. And the E1 is probably going to be one of them. And it may be the dominant product, but it's always a slow reaction. And so this will only become predominant if we do things to bias it so that this reaction is slowed down as well, and this reaction is less likely. So having a relative lot of water, having some acid present, having some heat, all of those things would tend to drive us toward the E1. Otherwise, the most likely scenario is you simply do the substitution, or if you don't have very much water around, then maybe you do nothing at all. The key feature of an E1 elimination, of course, is essentially you have to form a carbocation, and then your nucleophiles have to be weak enough such that you do an elimination instead of trapping the carbocation with the nucleophile. You will form a carbocation, so it has to be a reasonably stable carbocation, but then it just kind of sits there, and nothing really happens to it until it falls apart, and you make the double bond instead of a substitution product.